these notes are over Hooke's law. And so Hooke's law typically deals with springs, but it can work with any type of flexible material or like springy material, such as like a rubber band, a trampoline, and sometimes even wood. So when you step on a scale, or if you were to weigh a fish, you're usually using a device that involves a spring. Okay, so whether you compress, and this is like for old bathroom scales, or if you were to stretch the spring using a Newton spring scale, which is pictured here with the fish, okay, the natural reaction force of the spring is to bring the spring back to its natural length, its equilibrium position. Okay, so each spring is different, and so it's dependent on the material, the thickness, and the tightness of the spring, and that's going to affect how much force it takes to extend or compress that spring. Okay, so if you have a very, very thick spring, it's going to be much harder to compress or stretch it out compared to one that is very, very thin. You would more easily be able to stretch and compress it. When a spring is being extended by means of an additional mass, the net force on the mass will be zero when the spring settles to its new equilibrium. Okay, so what that just means, like here we have the picture of the fish hanging from the hook. Okay, eventually what's going to happen is that it'll all stop moving. Okay, so there's no acceleration on the fish, right? He's being held up by the spring on the hook, okay, and he's not continuing to extend the spring. And so because there's no acceleration, that means that there is a net force of zero, and we can use that later to help us solve some of the problems. Okay, so the amount of restoring force or spring force is equal to a spring constant times the distance that the spring is either compressed or extended. Okay, and I have here the different units for each. So spring force is given in newtons. The distance is given in meters, so be careful of that. If it gives you in centimeters or millimeters, you're going to have to convert it. And then the spring constant is newtons per meter. Okay, so this equation is going to work for any spring, provided that the force applied does not cause distortion or unraveling of the spring that is non-repairable. Okay, so a lot of the times with like thinner springs, you can cause distortion on it because it doesn't take a lot of force in order to kind of bend the spring so that it can't snap back to its original shape. Okay, so the value of the spring constant is going to be unique to each spring. Okay, and so basically what this constant or what the spring constant is telling us is how many newtons of force causes 1 meter of stretch. So that's why the units are newtons per meter. Okay, so a spring with large values for K, they're going to require more force to cause a certain amount of stretch or compression. If you were to complete the table, and you probably could have done this on your own using the formula, if we look, the center column is our force of the spring, or force applied. Okay, the spring constant is the first column, which is K, and then the last column is the stretch or the compression. So if we were to have, for example, the first one, 200 newtons of force equals 200 newtons per meter of spring constant, that would mean that our stretch would have to be 1 meter. Okay, and so if we look at like the next one, we have the force is 300, our spring constant is 600, so the 600 basically has to be halved in order to get the force, so that's why the stretch is only 0.5. Okay, and then like for the next one, the force is 100 newtons, the spring constant is only 25, so we would have to have 4 times that amount to get the force, so we have 4 meters. Okay, And then you can see the other ones as well. You can fill them in. So like I kind of explained at the very beginning, one of the many advantages of Hooke's law is that it's not just restricted to springs. So any kind of elastic material, so bungee cords, elastic bands, and like I had given the example of like trampolines, any kind of flexible materials such as plastic or wood also obey the Hooke's law to some extent. For example number 1, a fish of mass 12.9 kilograms is attached to a Newton spring scale that has a spring constant of 665 newtons per meter. Determine the stretch of the spring. Okay, so I'm going to first just fill in what data they already gave us. So I already drew the object with the mass inside of it, 12.9 kilograms. Okay, then it also gave me the spring constant, which is K, is 665 newtons per meter. Okay. All right, so the force that's acting upon that fish that's hanging from this spring scale is going to be the force of gravity felt by this fish. So 12.9 times negative 9.8. And I'm going to get that the force of gravity felt by this fish is negative 126.42 newtons. Okay? And so because when the fish is just hanging there, it's not accelerating up, it's not accelerating down, that means that our net force has to be 0. So that means that our spring force that we feel that that is pulling up on the fish has to be equal to the gravitational pull feeling down so that they cancel each other out to have a net force of 0. Okay, so it's going to be positive 126.42 newtons. Okay, so I'm going to just go ahead and fill that in here. Right, and it wants us to determine the stretch of the spring. Okay, so my equation, remember, is the spring force equals the spring constant times the distance of the stretch in this case. Okay, so plug in what I know, so 126.42 equals 665 times delta x. Okay, divide both sides by 665. And we'll get that delta x equals 0.19 meters. Okay, we could convert it to centimeters. It would end up being 19 centimeters, but this answer is correct as well. For example number 2, it says a composite hockey stick with a spring constant of 9,481 newtons per meter bends 5 centimeters during a slap shot. How much force did the stick apply to the puck? Okay, so it gives us a bend, the distance of its bending. The key thing, though, is that it gave it to us in centimeters. So we need to change that to meters. So in meters, it would be, we would have to move 2 decimal places. So 0.50 meters. Okay, because there's 100 centimeters in 1 meter. And it wants us to find the force of the stick applied. So the F of S equals our K times our delta X. So F of S equals 9,481 times 0.050. And we get that our spring force is 474.05 newtons. Okay, so that's how much the stick applied to the puck. For example number 3, a 61.2 kilogram bungee jumper jumps from a bridge. She is tied to an 11.2 meter long unstretched bungee cord and falls a total of 32.4 meters once her motion settles. Calculate the spring constant of the bungee cord. Okay, so here I have the person on top of the 32.4 meter bridge. Okay, to find our delta x, okay, the delta x is not the 32.4 because if you remember, the bungee cord is 11.2 unstretched. So this is equal to our 11.2 plus our delta x. Okay, so we would subtract 32.4 minus 11.2 to find our delta x. And so our delta x is 21.2 meters. Okay, and because this says that we're looking at the distance once the motion settles, that means she's not bouncing up anymore, bouncing up and down anymore. She has no acceleration. So our spring force is going to equal her gravitational force. Okay, so we can calculate her gravitational force as mass times acceleration. So 61.2 times the acceleration of gravity. And we find that the gravitational force felt by her is 599.76 newtons. Okay, and so because this is when she settles, our spring constant, this was negative, our spring force, sorry, not constant, spring force is going to be equal to the positive 599.76 because she's not bouncing up and down anymore, she's already settled. Okay, so acceleration 0. So if we go to, so that's my force of the spring. So now I can solve for K. Okay, so F of S equals K times delta X. Plug in what I know, so 599.76 equals K times 21.2. Divide both sides by 21.2. And I get that my K is 28.29 newtons per meter.